Hey everyone, Miss Butler here. I have a video for you on balancing equations. So this is one of the most important concepts in chemistry. And my goal is to teach it to you in this short little video here. So first of all, if we're going to balance a chemical reaction, we need to be able to understand what all of the little letters, numbers, and symbols mean. And so the first thing is you will see some symbols that tell you the state of matter, which is just extra information about the chemical. So if a chemical in the reaction is a solid, there will be a little S in parentheses after that chemical symbol. If the chemical is a liquid, it'll be a lowercase l in parentheses. A gas is a lowercase g. And if the chemical is aqueous, which means the chemical was solid, but then it was dissolved in water before the reaction occurred, you'll see a little AQ. So every symbol or every element formula will have a symbol, solid, liquid, gas, or aqueous after it. So it's not for the whole reaction, it's after each individual reactant or product. You will also see in a reaction that there is an arrow that separates the two sides. That arrow means yields or produces. So you start with some things and they are going to mix together, break bonds, make bonds to produce or to yield, and then the products, what the new chemicals that we have created as a result of the reaction. So let's take a look. Here's an example, and you can see that I have some more vocab. Everything on the left of the arrow, so this guy and this guy, those are called reactants. That's what we're starting with. And anything on the right of the yields arrow is the product. So this arrow means to produce or to make or to yield. So I'm starting with these things. They're going to react together, make bonds, break bonds to produce the product on the right side. Okay, you can have multiple products, you can have one product, you can have multiple reactants, you can have one reactant. We'll learn more about the types of reactions later this unit. Okay, a couple of things. I see that H2 is a gas, O2 is a gas, and H2O is a liquid. So that's what those little letters in parentheses are telling me. I also see that there are some coefficients. 2, there's an imaginary 1, and then a 2. And we're going to learn more about those and how to put those big numbers in the next couple of slides. But those big numbers are called coefficients. So we are going to be putting those coefficients into an equation so that it is balanced. But I'm curious, why do we need to do this? Why is this so important in chemistry? Why must we balance equations? The reason we have to balance chemical equations is because of the law of conservation of matter. And this is important. Let's put this in our notes. The law of conservation of matter states that matter cannot be created or destroyed. It can only change forms. So if I started with 2 molecules of H2 and 1 molecule of O2, I still need both of those after. They cannot disappear, poof into nothingness, and I cannot make more of what doesn't already exist. So can I rearrange them or change the form? Sure, I can make bonds or break bonds, have them bond with something different in a different way, in a different orientation. But I cannot destroy matter, it cannot disappear, and I cannot create matter out of nothing. So in a chemical reaction, the number of atoms must be conserved. So to follow the law of conservation of matter, the number of atoms must be conserved in a reaction, meaning that if I have 2 hydrogens on my left, I need 2 hydrogens on my right. If I have 2 oxygen on my left, I need 2 oxygen on the right. So let's take inventory. Here's that balanced equation we already looked at. It is already balanced, so let's prove it. I'm going to prove that it's already balanced. So on my reactant side, the only capital letters or elements I see are hydrogen and oxygen. And then on the product side, hydrogen and oxygen. Now I'm going to count the atoms, just like we learned how to count. There are 2 little hydrogens here, but 2 of those molecules, so 2 times 2 gives me 4. There's 2 oxygens and a 1 in front. 1 times 2 gives me 2. So there's 4 hydrogen atoms and 2 oxygen atoms on this side of the equation. On the product side, this 2 in front applies to the entire chemical. So 2 times 2 gives me 4 hydrogens, and 2 times this little imaginary 1 gives me 2 oxygen. So I have 4 hydrogen, 2 oxygen, 2 oxygen. This is a balanced equation not because everything is equal amongst itself, but that hydrogen equals hydrogen and oxygen equals oxygen. That's what we mean when we say a balanced equation. So how do we balance equations? Well, you're going to be given reactions without those coefficients in front. So these big numbers will not be there in front when you go to balance an equation. Here are the rules. Coefficients can only be put in front of a chemical formula. For example, H2O, I can only put a number in front of the entire thing, which means it applies to the hydrogen and the oxygen. What I cannot do is I cannot say, oops, sorry, where's my pen? There we go. H2O, let's say I need 3 oxygens. I can't put a big 3 in the middle of the formula. It can only go in front like this. So this is not allowed, no big numbers inserted or smooshed in the middle of a chemical compound. Okay, when we do put the coefficients in place, they multiply by the subscripts of the individual atoms. So for example, 4 CO2 means there are 4 times 1 carbons, 4 carbons, and 4 times 2 oxygen, 8 oxygen. So this formula for CO2 gives me 4 carbons and 8 oxygens. So here are my tips for balancing. First, I always start with any unique element. So maybe there's only one of them on either side of the equation, whereas something like hydrogen and oxygen sometimes are in multiple reactants and multiple products. So we usually do those last. So unique elements for something that maybe catches your attention, stands out. It's only in one compound on the left and one compound on the right. If there are the same polyatomic ions on both sides, I actually treat them as a unit and as a group and balance those instead of breaking it apart. For example, the polyatomic phosphate PO4, if that's in a formula on one side and I also have it on the other side, what I'm going to do is I'm going to balance how many PO4s over here, how many PO4s over here. I have 1 PO4 on this side because there's no number outside the parentheses. I have 2 on this side. That's a lot easier than saying how many P's on the left and how many P's on the right, how many O's on the left, how many O's on the right. Instead, I say how many PO4 groups, and I can show you an example of that. And then finally, you should check your answers. You can know if you're right or wrong before you even turn anything in because you can double check that all of the atoms on the left are equal to the number of atoms on the right for all of those capital letters. And then finally, use pencil or whiteboard. This is a lot of guess and check, or sometimes you put a coefficient in front because it works for a minute, and then you end up needing to change it to accommodate a different element or a different polyatomic. So there is some erasing happening. That does not mean you're doing it wrong or bad. It just means that you're going through the process, and it's a lot of making a coefficient work for right now and then fixing it later so that everybody is balanced. So let me show you an example. This is an unbalanced equation because I don't have any coefficients in front of any of the reactants on this side or products on this side. What I usually do for taking inventory is I draw a line right under the arrow because that separates the reactants and the products. And now we're going to take inventory. And the way I do that is I start on my reactant side and I see that there's an iron, Fe, and I see on my product side there is an iron. I see a potassium and a potassium. And then I also see nitrogen and oxygen, but this is a polyatomic called nitrate. It's on my polyatomic ion list, and because the nitrate polyatomic in the ratio of NO3, 1 N and 3 O's, does not change, I am going to just count how many polyatomic nitrates I have on either side instead of separating it into N's and O's separately. It'll make it easier. So now let's count. To start, I have 1 of the Fe, I have 1 of the potassium, and because of this 2, I have 2 nitrates. On my product side, I have 1 Fe, 1 K, and there's no number outside the parentheses, so 1 nitrate. Now we're going to start by looking for anything unique or anything that's not balanced. So 1 and 1, that's balanced. 1 and 1, that's balanced. So the only thing that's not balanced is the nitrate, and that is kind of unique. It is something that's jumping out and catching my eye because it's that group of atoms. So I need to get 2 nitrate groups on this side. The only way to do that is by adding more of what's already there. So here's what I'm going to do. I'm going to put a big 2 in front of this whole chemical. What that does is now that gives me 2 of the nitrates, because this 2 applies to this guy, but it also gives me 2 of the potassiums. So I think of this as a back and forth. Now we fixed our nitrates, but now we need to go back to this side and fix our potassiums. How can I do that? Well, that's pretty easy. All I have to do is add a 2 in front of here. Now there's 2 potassiums, and that didn't change anything else. So we are now balanced. 1, 2, 1, 2. Okay, I need everyone to take a deep breath with me. All right, when your teachers are feeling nice, they will give you a unbalanced equation like we just looked at with all of the formulas. But when they're really trying to push you and make you smarter and make you grow, instead of giving you the formulas, they're gonna give you the chemical names. So we have to tap way back into our brain with ionic bonding and covalent bonding to remember how to go from the chemical name to the chemical formula. So here's a little bit of a review, but if you need more help with this, please go to office hours and see your teacher. Okay, so the first thing is I always write the reactants and products first with using all the naming rules because we can't balance if the little subscripts are wrong because we write our formulas wrong. So I don't even worry about the big numbers until the very, very end. So I just need to write the formula for every reactant and every product carefully using the naming rules. What are some of the naming rules? Well, if your substance that you're trying to write is a compound, it's going to either be ionic or covalent. If it is ionic, it's because it has a metal and a nonmetal, or it has a metal and a polyatomic ion, or it has a polyatomic ion and a nonmetal, or a polyatomic ion and a polyatomic ion. Okay? How do I write the formula? Well, we need to crisscross charges. So let's say I have metal A with a +2 charge, nonmetal B with a -3 charge. I get those charges from the periodic table, or if it's a polyatomic, I get the charges from my polyatomic ion list. When I crisscross, the 3 goes down here, A3, the 2 goes down here, B2. Those are subscripts, small numbers. We'll worry about the big numbers at the end. So that's how we crisscross. If it's any of these combinations, that means it's an ionic compound. If it is a covalent compound, that is going to be a nonmetal bonded with a nonmetal, and they are going to have prefixes in the chemical name, like carbon dioxide, 1 carbon, 2 oxygens, right? Or it's going to be diphosphorus pentoxide, 2 phosphorus, pentoxide, 5, penta is 5 oxygen, P2O5. Okay, so for compounds, you're either going to crisscross the charges if it's any of these combinations together, or you're going to use prefixes if it's 2 nonmetals. Those prefixes tell you exactly what the little subscript should be. Okay, the other possibility is it could be an element all by itself, not 2 things bonded together, just one solo guy. Elements do not get any subscripts, any small numbers, unless it is one of these 7 diatomic elements. And the way I remember these is the phrase hike, bro, need, cliff, bar. Don't worry about the bar part. But if I'm going for a hike, bro, I need a cliff bar. So hydrogen, bromine, oxygen, nitrogen, chlorine, iodine, and fluorine. If I just say magnesium reacts with oxygen, magnesium's an element all by itself, no little subscripts, but oxygen is always O2, never O by itself. Okay, and that's anytime I just say oxygen. If oxygen's part of a compound, then we will do what's appropriate with subscripts or with prefixes or with crisscrossing. But if I just say oxygen by itself or iodine by itself, I'm talking about these. Okay, then after we write all of the reactants and products, we can add the states of matter, solid, liquid, gas, aqueous. How are you supposed to know if something's a solid, liquid, gas, or aqueous? Well, there's going to be clues in the description. If they use the word solution, solution is a synonym for aqueous. Okay, if they say metal or precipitate, those are synonyms for solids. Vapor or bubbles are synonyms for gas. So that's how we figure out solid, liquid, gas, or aqueous. Or they will just tell you liquid water reacts with, and now we know it's a liquid. Okay, and then now that all of these steps are done, we can balance by taking inventory like we learned how to do on the last problem. Balance, meaning we are putting the big coefficients in front. Taking inventory, meaning we're counting how many are on either side to keep track of all the elements. So if you are scratching your head saying, Miss Beller, I am ready to practice balancing, but this naming stuff it was hard for me the first time and I'm still not remembering, this flow chart might be something for you to look at, and it could be of help. So when I say, is it binary, I'm saying, are there only 2 capital letters? Okay. If yes, it has only 2 capital letters, I'm asking, does it contain a metal? If it does contain a metal, then we're going to use ionic rules where we crisscross, and there's some descriptions and examples. If it does not contain a metal, that means it's covalent, and we're going to use the prefixes to tell us the subscripts. If it has more than 2 capital letters, that is ionic, but it means there's a polyatomic ion. So this is ionic because it's a metal plus a non-metal. These over here are ionic because they have something plus a polyatomic ion, or a polyatomic ion plus something else, like metal, non-metal. And then the other guys down here are covalent because they are 2 non-metals. So this flow chart might be a good help. Oops, non-metal, that's an N. This flow chart might be a good help for you when you're trying to review naming, especially if there's polyatomic ions involved. There's also some polyatomics listed here, but I've also included a list for you. Here is a list of the common polyatomic ions that you tried to memorize. If these are not written on the back of your periodic table, you should definitely write them. If it helps you, because these are the ones we would crisscross with something else, you can put the charges outside of the parentheses. So sulfate would be like SO4 with the charge outside, because the charge is what we crisscross. The SO4 formula stays the same. So that might be helpful if you want to write them in that format on the back of your periodic table. All right, so let's try this word equation together. It says, hold on, let me fix my iPad. All right, it says calcium metal reacts with, so calcium metal. Calcium is an element all by itself, okay? And so I'm going to look at those steps. I said if it's an element, it does not get any subscripts unless it's one of the Hike-Bro-Need Cliff Bars: hydrogen, bromine, oxygen, nitrogen, chlorine, iodine, or fluorine. Calcium is not one of the Hike-Bro-Need Cliff Bars, so I'm not going to give it any subscript, no number, and it said it was a metal, and metal was one of my clue words for solid, okay? So calcium metal reacts with, that's a synonym for put the plus sign. So calcium is going to react with, and it says aqueous iron 3 nitrate. So the aqueous, or iron 3 nitrate, is the chemical name, iron 3 nitrate. The aqueous is just telling me the state of matter to put after we write the formula. Okay, here's what I see. Iron 3 and nitrate. Iron is a metal, and nitrate is one of my polyatomic ions that I tried to memorize because it ends with 888, so it's on the back of your periodic table. So anytime we have a metal or a polyatomic ion, that tells us it is ionic. So we are going to need to crisscross the charges. Well, iron is one of those elements in the middle of my periodic table. I don't know the charge by looking at it, so I use the Roman numerals to help me. It's +3. Nitrate is on the back of my periodic table. It has the formula NO3 and the charge -1. So when I crisscross, the 1 goes down to the iron, the 3 goes outside of the parentheses. So I get Fe1 NO3 3. You do not need to write this little 1, but if it helps you because it reminds you that. So if you need that one because it reminds you that you crisscross, that is totally fine. You can leave it. And then they told us that it was aqueous, so I'm going to put aqueous. Okay, it says to produce. That's a synonym for the arrow, so I'm going to draw my yields arrow. An aqueous solution of calcium nitrate. So that has aqueous and solution. That helps me with the state of matter. Calcium nitrate is my chemical formula, or chemical name. Calcium is a metal, and nitrate is a polyatomic ion, so we need to crisscross. I find calcium on the periodic table. It has a charge of +2. Nitrate is a polyatomic ion. It always has the formula NO3 and the charge of -1. When I crisscross, the 1 goes down here, the 2 goes on the outside. So Ca1, NO3, 2, and they told me it was aqueous. And then it says they produce solid iron, and solid iron. So plus, so and is my plus sign. Solid iron, well, I know it's a solid. Iron is an element all by itself, and it's going to be solid. We don't need any numbers because when it's an element, we ask ourselves, Hike-Bro-Need Cliff Bar. And iron is not one of my Hike-Bro-Need Cliff Bar elements, so no little subscript. Okay, so now I am ready. I've written everything properly. We have to do that part first before we put big numbers in, because if these small numbers are incorrect, then the whole balancing is going to be a waste of our time. Sorry. All right, so I draw down my line. We're going to take some inventory. I see calcium on both sides. I see iron on both sides. And the polyatomic nitrate on both sides. So let's count. There's 1 calcium, there's 1 iron, and there are 3, because of outside of the parentheses, 3 of the NO3 groups. On this side, I have 1 calcium, I have 1 iron, and I have 2 of the nitrates, right? So because of that little 2, there are 2 of the NO3 groups. So everything, now let's look, is balanced. Ca is balanced, Fe is balanced, just the nitrates. We have 3 and 2. So here's what we need to think about, because I have less on this side, so my instinct is to put a number here. But if right now there's a 1, if I put a 2, that will make 4 nitrates. And there's nothing I can multiply 3 by to get 4. So we need to think about what the great least common factor is, or whatever that expression is called in math class. Essentially, what can I multiply this one by to get a number, and what can I multiply this one by to get a number where they are equal? Well, I know 3 and 2, that least common factor or greatest common factor is 6. So I'm going to say a 3 on this side. Let me show you. Here's what that does. 3 times this 2 gives me 6. It also gives me 3 calciums, and I'm going to worry about that in just a minute. I know we messed up the calcium. That is okay. We're going to worry about it in a second. On this side, I'm trying to now get 6 of the nitrates, so I put a big 2 in front. 2 times the 3 that's down here gives me 6, and that now gives me 2 times 1 iron, so we messed up the iron. Okay, let's fix the iron that we just messed up. So I'm going to go over to this side, and I need to put a number here so that they are equal. That means I need to put a 2. That's 2 iron. And now let's fix finally the calcium. I have 3 on this side, so let's go over. What do I need to put in front? Well, I need to put a 3, because 3 times 1 gives me 3. Does everything match? 3, 2, and 6? Yep, we are balanced and done. Okay, here's what I would like you to do. I want you to try this one. Solid magnesium metal, so that's your first thing, reacts with, so plus oxygen gas, so that's your second thing, to produce, so that's your arrow, right? We're making, and then solid magnesium oxide. So we do have an ionic chemical there. I want you to pause the video and try this one on your own. I'm going to put the answer up for you to check in 3, 2, 1. All right, so I've written the equation. Solid magnesium metal. Magnesium is an element, so there's no subscript. It is not one of my Hike Bro Need Cliff Bar, so no subscript. It reacts with, so plus, and then oxygen gas. So I put the gas symbol. Oxygen is an element by itself, but it is one of my Hike Bro Need Cliff Bars. It's the O bro in bro. So I need a little 2 for this element. So any of the Hike Bro Need Cliff Bars get a little 2. Any other element by itself does not. And then it says to produce, so that's my arrow, and it says magnesium oxide. Well, magnesium oxide is a metal with a nonmetal, so it's ionic. Magnesium's charge on the periodic table is +2, oxygen's -2. When I crisscross, I get Mg2O2. 4 ionic compounds, when they are the same, we are going to reduce or simplify them. And so I got MgO. And so MgO is my solid. Now that we have everything ready, we can start to balance. I have magnesium on this side, and there's 1. I have oxygen on this side, and there's 2. I have 1 magnesium on this side to start and 1 oxygen. So the only thing that doesn't match is oxygen. So in order to make those match, I need to have 2 on this side. I add the 2, and that gives me 2 oxygens, but it also impacts the magnesium. Now there are 2. So how can I fix that? Well, I can fix that by putting a big 2 in front here. So my balanced equation is 2, 1, 2. All right, couple of things. If you need a little more information on balancing, or just hear it a different way from somebody else besides me, there's a link on the agenda, and there's also a video on law of conservation of mass. Those are optional. It's just if you need them. Here's what I would like you to do. Today, you're going to answer questions 1 through 8 on this balancing equations practice number 1. So these are from your notes, and then 3, 4, 5, and 6. 7, and 8, you are balancing. For 7 through 19, I did not give you room to take inventory, but you should do it on a separate sheet of paper if you need help. So basically, my thoughts are by the time you get to 7 and 8, some of you will be ready to just look at it and go back and forth and balance without taking inventory and showing those steps. Some of you will need to take inventory for every single problem still. That is fine. Use a whiteboard, use separate paper, and then just record your answers here when you're done. Okay, so you're doing 1 through 8 today. On Wednesday, you will do 9 through 14, and Thursday, you will do 15 through 19. That way, you've done 19 balancing problems to be ready for your progress check on Friday. So none of the worksheet problems are word equations. All of them are just straight up balancing. That is how your progress check on Friday is going to be as well. You won't have to write from the word equation to the equation and then balance. It's just balancing like this worksheet. If you need more help than the 19 problems that are provided, this link will also be available on Canvas, and it's basically like a game that you can practice. It gives you different equations to balance, so lots of opportunities to practice before your progress check. We will continue to practice the word problem ones because you will have to do those by the end of this unit. So I'd rather show you now and do a little bit, maybe some warm-up questions with them to give you the practice. But your goal at this point is just let's figure out the balancing piece and then come in for help if you need help going from the word equations to the formulas. All right, see you guys later.